A lot of people have probably heard about Kubernetes. It's been, quite the buzzword lately in DevOps and deployments and everything. And I think if you start diving into Kubernetes stuff, you really quickly end up in operational things. And as an app developer, it makes you go, well, that's all fine and good that my company's going to do Kubernetes, but what does it mean for me? So that's what this talk is about. How do developers make use of the features of Kubernetes? So, as Carmen said, I am Jeff French. I'm the principal consultant at MoonSwitch. We're a DevOps and cloud migration consultancy here in Oklahoma City. Well, technically in Norman, but anywhere in the area. And you can follow me on Twitter at Jeff_French. So, let's dive right in. What is Kubernetes? So Kubernetes comes from a family of products called container orchestrators. Okay? A container orchestrator, basically, its whole job is to take Docker containers and run them on some computers somewhere, generally in the cloud, maybe in a data center. It's not the only one in this space. Some of the other ones in this space are Docker Swarm, Apache Meso/DCOS, HashiCorp Nomad, to name a few. And they all try to solve relatively the same problem. You have apps in Docker containers that you need to run somewhere, and they're going to find somewhere for them to run within the resources they have available. So, let's start at the beginning. For Kubernetes, the things that it tries to schedule, the containers, are grouped in something called a pod. So, a pod is a collection of containers and volumes. So it's a nice little definition of things that says, here is one or more Docker containers that make up some unit of work for my application. Here are the environment variables that that application needs. Here are some configuration files. Here are volumes that it needs to read and or write to. Here's the ports that it's going to communicate on. So that's what a pod is. It's kind of the basic unit of work in Kubernetes. So you define a pod in Kubernetes YAML like this. So we can see here we've got a nice simple YAML definition. The kind is a pod. It's got a little bit of metadata that says, hey, here's the name of this. Here are some labels that can help group pods together so you can operate against them, as a group. And then we define a really simple container here. We give it a name, a command to run. In this case, it's just a BusyBox container that's just going to say, hello, Kubernetes, and then sleep. We have mounted a volume on here, so it will have access to this as a local disk that it can read and write to at this path /test_pd. And then the definition of the volume that's going to be mounted in that location is given down below. So we can say, okay, well, on the host, it's going to be a /data directory. There's a lot of different types of volume mounts that you can use. Some are temporary file systems, some are permanent file systems, or you could potentially mount an EBS volume to the host and then mount that into your pod. So that's the basic unit of work. Now, the next thing that you need, so we've got an application that's running. We probably want to get some kind of traffic into that application, usually over TCP, HTTP. And so a service helps route traffic to a set of pods, all right? So given any number of pods that are running for a given application, this service is what's going to accept traffic and distribute it out to those pods, which is really cool because as you start to scale up, the way that you scale an application in Kubernetes, which we'll get into a little more detail at the end of this, you add more pods horizontally to handle additional traffic. But you don't want to have to manage a separate port and IP and endpoint for all of those things. You just want the traffic to go to one place and have it decide where the stuff goes. This is a form of basic routing and service discovery in Kubernetes. The way that it works for service discovery is that when you create a service in a particular namespace in Kubernetes, you get this kind of a DNS resolving within the cluster. So you'll have whatever the name of the service is, dot the name of the namespace it's running in, dot cluster, dot local. So you can have sort of a well-known convention that says, oh, okay, I know that our API is always going to be running under a service named API.default.cluster.local. So if I've got a pod that's, say, running a front-end web application that needs to talk to our back-end, not from the client side, but on the server side, then it can use that and it will be able to find those pods and actually communicate with them within the cluster without having to go actually know which host they're running on, which port they're communicating on, or any of that stuff. So if we look at a simple service definition, we've defined a service here named myService. An important part of the service definition is the selector here. So this selector tells this service how to find the pods that it's supposed to communicate with. So we'll have a set of pods that will have a label applied to them. As we saw back here, you can have labels on your pods, such as my app. That on me, I made this one all lowercase, and I made my selector over here camel case. But you get the idea. This service is meant to go find any pods that are running with that label and route traffic to them. And in this case, it's routing HTTP traffic on TCP port 80 that is going to the pod at port 9376, and HTTPS traffic, TCP 443 on 9377. So this is going to handle basic routing of any requests that come in throughout the cluster to get this traffic into your pod so that you can actually do something with it in your application. So that's great. That's how you can address a service locally inside the cluster, but probably your users of your application are not inside your cluster. They're somewhere outside on the internet, right? So that's where an ingress comes into play. An ingress is a Kubernetes resource that is designed to expose a service to the outside world so that you can route actual internet-based traffic or LAN-based traffic into this cluster and have it find your service and then ultimately find your pods. So an ingress looks like this. We've got a name, and down here in the spec, we define a host. So this is going to end up being a publicly routable host name that I want it to respond to. And then on the paths, I'm telling it, okay, well, go find a service named GitLab Unicorn, and for its port, pass this on. And you can define multiple things so that you could essentially have one front end that then routes different paths or, you know, on your URL into different services inside your cluster. So that's pretty cool. And then some of the really cool things that you can do with Kubernetes here is you see all these annotations I've got up here. We've got these Kubernetes ingress class and an ingress provider and TLS and all these fun things. So what those are is there's all these different things that you can kind of put into your cluster on a Kubernetes cluster called operators that help you manage your application, manage your infrastructure. And two of them that are being used or that are using these annotations are an ingress controller from Nginx. So what that does is it says, okay, well, I'm going to set up Nginx for you, and it's going to receive all your traffic. Whenever you define an ingress like this, it's actually going to be coming into Nginx, and then Nginx is going to turn around and route it out to your different services and pods. And what's cool about that is that you get all the fun stuff that you like and love about Nginx, so that you can now configure it. As you see, I've configured some of these, some custom Nginx settings for this particular ingress just by adding these annotations onto my pod. I can set the body size, a proxy connect timeout. Almost any setting that you can put into Nginx, you can define with annotations if you're using the Nginx controller and the Nginx ingress controller on Kubernetes. And then another fun one here, so that's what this is. This tells the Nginx ingress controller whenever a new ingress is created, it reads these annotations and says, oh, okay, I should manage this, or I shouldn't. And then the next fun one here is this TLS acme equals true. This is because this came from a cluster where I was running cert manager. Cert manager is an operator that interacts with Let's Encrypt to automatically request, validate, and renew SSL certificates for your ingresses. So the fact that I simply put this one little annotation on my ingress is going to let the cert manager operator see that, read it, and say, oh, okay, I know what to do. I'm going to go request an SSL certificate with this host name, and I'm going to store it in, and I'm going to also have additional hosts. You can add multiple hosts here if you want to have additional host names, subject alternate names. And it's going to store that TLS certificate that it gets back in this secret in Kubernetes. And what's really cool is that it's going to store that with its expiration date as well. And then it's going to have essentially a cron that runs every hour or so like that, and looks at all of the certificates that it's currently managing and says, oh, hey, this one's about to expire in 2 weeks or a week or whatever. I'm going to go ahead and renew it. So it goes ahead and proactively renews that certificate for you, replaces it on your running pod, and you don't even have to think about it. So by putting this one little annotation on my ingress with a cluster that's running Cert Manager, I get nice, well-trusted, let's encrypt certificates for free, always up to date and renewed automatically, and I don't have to think about it. So we can have a nice, secure application without all the hassles of renewing certs or forgetting that a cert's going to expire and all your users are the ones who let you know. We've been through that. We don't want to do that. So let's wrap all the stuff we've covered so far into this one nice little diagram. We've got our Kubernetes cluster out here. We've got the internet out there in the proverbial cloud. And traffic comes in. It hits the ingress. In this case, it's an Nginx ingress. That Nginx ingress says, hey, I know what to do with this traffic. I'm going to route it to a service. And that service says, oh, OK, cool. I know which pods I'm routing traffic to, and I'm going to distribute it amongst those pods. I think by default, it's round robin, but there are a few different things you could put on service to control how it selects pods to route traffic to. So that's the basic request flow. So that's cool. Well, what if what I'm running is more of a kind of one-off task? Well, Kubernetes has something for that too. They've got jobs. A job runs a set of pods until a successful completion, or what it thinks is a successful completion. So these are great for things like, say, a database migration. You don't need that to be running all the time. You just need to run it once per deployment. So if part of your deployment into your Kubernetes cluster includes creating a job that's going to run a database migration for you, that job is going to provision a pod inside the namespace. It's going to let that pod run with whatever configuration you've supplied to it and whatever commands you've told it to run. And it's going to run, and if that pod errors out, then the job definition is going to turn around and say, well, that didn't work, let's try again. And it's going to spin up another one. And it's going to keep doing that until it either hits a predefined set of failures, or if you've allowed it to fail, then that's fine, or until it gets a successful completion, meaning the pod runs all the way until it's done and the command exits without an error, which is great for things like database migrations or other one-off tasks. You can also set up cron jobs in Kubernetes now, where you can give it a cron-like definition, and on whatever schedule, it will create those sets of pods and run them to completion, which is a great way to handle a lot of cluster maintenance-y type of tasks, or things that just need to happen on a schedule to, I don't know, maybe run some data warehousing job or something like that, right? You say, okay, cool, our application's running in Kubernetes, but once every 4 hours we need to warehouse data off to the SQL Server for reporting purposes or analytics. So you could have that set up as a Kubernetes cron job. So here's what a basic job definition looks like. This one is really cool because it's going to calculate pi to 2,000 places, because we all need our applications to know pi to 2,000 places, right? But it's a basic definition, and it says, okay, here's the container, here's the Docker image I want you to use, here's the command I want you to run. Restart policy of never, meaning like, well, if it fails, just let it fail. I don't want you to keep trying. And the back-off limit of 4. I'm sorry, so the restart policy of never, meaning if the pod exits with an error, if it can't start it, try 4 times. So we talked about your deployment into Kubernetes, right? So we've got all these objects so far that we have to create, these pods and services and ingresses and jobs. Well, in the early days of Kubernetes, you would manage a group of pods that you wanted to scale with a replica set. And technically you still do, but you don't manage those directly anymore. You use a deployment now. Because a replica set's job is to scale a number of pods based on some set of rules. And the problem that you run into in managing those directly is that when you go to actually deploy the next version of your application, you've got to scale one replica set down, take it away, scale the other one up, and all of this results in downtime for your application. So they introduced a nice object called the deployment object. And A deployment object is kind of a higher level object over replica sets, and what it does is it says, hey, I'm going to manage these replica sets for you. And I'm also going to take a definition about how you want your deployments to be handled, whether it's rolling upgrades or anything like that. And what this allows you to do is create a deployment, which we'll look at here in just a second, that has a whole spec for what the pods should look like. And that deployment is then going to say, okay, cool, I'm going to spin these pods up according to the instructions you've given me, and they're going to be running. But then, when you come in and deploy a new version of this deployment and update the actual deployment object itself, it says, oh, okay, great, I'm going to follow the rules that you've given me for how to switch your pods out. So you can have a zero downtime deployment, your users don't even notice it, except all of a sudden, hey, I got a new feature. So here's what deployment looks like. Very basic one here. We give it a name, we give it some labels. I'm telling it, all right, I want you to run 3 replicas of the pod that I'm going to define down here. So it's going to create a replica set with a scale factor of 3. It's got a selector, and this is important, kind of like with our services. This tells the deployment how to find the pods that it's supposed to manage. So each one of the pods is going to have these labels on it, and the deployment says, okay, whenever I go to start replacing old pods with new pods, I'm looking for these labels to do it. All right? So as we see right below it in this template, this is the template of a pod spec. And we give it the nice Nginx label. And then we tell it the rest of our pod spec. And this can all look exactly like basically everything that's in this pod spec here can go in our template pod spec as well. There we go. So it defines a set of pods, which can be 1 or more containers, 1 or more volumes, all these things. And then we tell it, go manage those pods for me so that whenever I deploy them, you handle taking, if I've got 3 pods out there, take 1 down, put 1 up. Take 1 down, put 1 up. Take 1 down, put 1 up until you've replaced all of my pods. So here's the types of deployment strategies that you can configure on a deployment object. One would be max unavailable, the other would be max surge. So this is going to depend on what kind of resources you have in your cluster and whether it's better for you to spin up more resources or to stay under a certain limit. But if you have max unavailable, you're giving an absolute number or a percentage of pods that can be unavailable at once during deployment. So if in our previous pod, if I had deployment of 3, and I tell it max unavailable of 1, then it's saying, okay, I can never have more than 1 pod down as I'm swapping things out. On a max surge, it's an absolute number or percentage of pods that can be created in excess of the desired number on the deployment. So this is saying, well, no, if I said 3, then you start creating extras before you take my other ones down. And this all kind of depends on your application and how it handles traffic and state and all these kinds of things, and also just the amount of traffic you typically have during a deployment. So here's some kind of worked examples on these things. Given a deployment with replicas equal 10 and a max unavailable equals 3, then our deployment can drop as low as 7 pods that are still active and serving traffic while 3 new ones are spinning up. And then it can, once those 3 come up, then it can drop up to 3 more until it's completed updating all of the pods. On a max surge, it lets it surge as high as 13. So if I've already got 10 running, it says, hey, we can't handle our traffic, going, our traffic is too high to start pulling pods down. So what I want to do is spin up extra pods until they're available, and then we can take the other ones down. That way we never dip below 10 pods available. So I promised we would get into scaling. Here we are. The horizontal pod autoscaler scales out a deployment based on observed CPU utilization or other metrics. CPU probably being the most common one. You could also do memory. You can also now do custom metrics with Prometheus and things like that, where you can define almost any metric or API you want it to hit, even external things, and based on the results of some API call, this horizontal pod autoscaler will handle scaling your pods horizontally. So what that means is exactly this. I start with a deployment that says I've got replicas of 3, and then I deploy a horizontal pod autoscaler that says, well, I want to say a minimum of 2 pods and a maximum of 10. And I want it to be based on 80% CPU utilization on my target pods. So what the horizontal pod autoscaler is going to do is basically start polling the metrics server, looking at its set of pods that it's managing and saying, well, is the average CPU usage across these pods greater than 80%? If so, then I'm going to start adding more pods to scale it up. And then once it starts dripping below 10% for or 80% for a certain cool-off period, it will start pulling those pods back down. So this way you get kind of automatic elasticity within your cluster. This becomes really, really cool because you can couple this with a cluster autoscaler. And this is where you can start to really take advantage of the elasticity of cloud computing, right? We've been promised all along since cloud computing became a thing, well, yeah, you only pay for what you need. And then we started working on it and found that, oh boy, especially in the early days, what that meant was somebody had to say, well, we need more, spin up another EC2 instance. Oh, we're using too much, take down an EC2 instance. And we got a little bit more automation around those. Kubernetes has really kind of helped take that a step further. So if you were, say, running in GKE or AWS or Azure, in any of their Kubernetes things, you can put a cluster autoscaler on there. And a cluster autoscaler, its whole job is to say, well, looking at all of the pods that I'm supposed to be running, do I have enough room to run all of them on the nodes that are available in my cluster? And if the answer to that question is no, it will start adding nodes and then redistributing the workload. And likewise, it will also scale down by saying, well, if I've got a workload that is way under what the max capacity of my cluster is, I'm going to look at taking those pods and consolidating them down into the number of nodes they'll fit on and start removing nodes from this cluster to save you money. So when you couple a horizontal pod autoscaler with a cluster autoscaler, you can start with a nice small cluster, and then as your app starts getting a bunch of traffic and you get really popular and all of a sudden you're trending on Hacker News and all this traffic's rushing in and it sees your CPU go up, then the horizontal pod autoscaler says, cool, dish out some more pods. But then the cluster scheduler says, I don't have any room to put these pods. Okay, I'll add a node. So it adds a node, and then it puts those pods there. And all of a sudden, your app just scaled itself up pretty quickly all by itself. And then, the Hacker News cycle goes to somebody else, and all your traffic drops back down, and your cluster consolidates itself back down, so you're not spending all this extra money. So this is typically how you can, this is one way to just create from the command line a cluster autoscaler. You say, hey, autoscale this deployment, here's the deployment name, here's the target CPU percentage, and here's the min and max I want you to run. Here's kind of a illustrated example of it, all right? So we've got a service feeding traffic to pods, and we've got a horizontal pod autoscaler, which is managing a deployment, and that deployment is managing a replica set of these pods, all that fun operational stuff that you don't have to worry about. And the horizontal pod autoscaler is checking the metrics API to see what metrics it's getting from those pods. Right now, everything's low, and that's good. And then, boom, we get hit with a big spike in traffic. The horizontal pod autoscaler tells the deployment to scale up. The replica set then adds a few more pods. Traffic magically starts flowing because the service is already sending traffic to all the pods with those certain labels, and your application is scaled. All right. Okay, Q&A time. Sorry, we had to go through this really quickly. The keynote ran over. Yes?
So one of the examples you just showed had PHP Apache running in some pods. A lot of PHP apps have stateful sessions and things like that. How does that interact with moving a pod from one node to another, or scaling up, scaling down? How does that affect sessions?
So if you have a very stateful workload, there are other ways besides deployments to run pods in Kubernetes, one being a stateful set. And so what a stateful set does is it creates pods that have a very finite order in which they come up and go down, and Kubernetes takes extra care in the way it manages those. So I don't know much about PHP. That was just a rough example that I most likely copied and pasted from somewhere on the internet, to be perfectly honest, and didn't think it through on that perspective. But yeah, there are ways to manage stateful workloads. Now, some people like to use stateful sets to run stateful workloads like, say, databases in your Kubernetes cluster. That's probably okay in your development environment. Please don't run your production database in Kubernetes yet. It's there's a lot of people working toward making that something that can actually work, but in my experience, it's not there yet. So take that for what you will for stateful workloads. Yes?
You spoke about the cluster autoscaler.
Uh-huh.
So let's say I'm using autoscaling groups on AWS.
Uh-huh.
So how does that
So yeah, the question is for the cluster autoscaler, if he's using autoscaling groups on AWS, how does that jive together? Well, actually, whenever you run Kubernetes in a cloud provider like AWS, DigitalOcean, Google Cloud, they all have these cloud provider, essentially shims, that help the Kubernetes kind of standard framework run on that particular cloud. So in the case of AWS, the way that the cluster autoscaler works is by actually managing an autoscaling group for you. So you essentially end up having to create a IAM profile for your Kubernetes nodes that has permission to manage a particular autoscaling group with a particular set of tags. And whenever the cluster autoscaler notices that it needs to add more nodes, the way that it actually does that on AWS is by incrementing the autoscaling group and having it add nodes, or decrementing the autoscaling group and having it remove nodes.
So I'm guessing EKS does this.
Yes. Yeah, because, well, in EKS, which is Amazon's kind of managed Kubernetes thing, they only manage really the worker nodes, and you're basically responsible for, or they manage the master nodes, and you're responsible for managing the worker nodes. They have some CloudFormation templates that help, or you can do it with Terraform or something like that, but you kind of are on the hook for spinning up your worker nodes or using some of their tooling to do it for you. But ultimately, you're kind of managing a set of nodes almost on your own that are the actual workers. So, yes?
Besides being able to switch like cloud providers, what would be the main advantages of using Kubernetes?
I would say that, so the question was, what if you're not worried about trying to take your workload from one cloud to the next, what's the advantage of using Kubernetes over using something native to that cloud provider like EC2 instances or whatever? I would say that part of that would probably just be the ecosystem. Kubernetes has gotten popular enough that there's a good ecosystem of people developing tooling around it and tooling for it to handle things like deployments and DNS updates to your outside providers and things like that. So that's one of the areas I found it to be really common. And then just as a developer, the idea of standardizing your tool set on Kubernetes just because your current company uses AWS, right? And then you go to the next company and they use Google Cloud. But if both of them are using Kubernetes implementations, your skill set is more portable, is one of the things I really like about it from a developer perspective. All right, yes? Great question. So the question was, we've got all this auto-scaling on the pods, but your ingress controller look like a single point that is either going to have to handle all the traffic or fail or scale itself. Yes, you can scale your ingress controller in multiple ways. You could actually put a horizontal pod auto-scaler on the ingress controller itself so that it is looking at its own traffic and saying, hey, I need to add more ingresses because I'm too busy. You could have an ingress controller that is for your entire cluster, so there's one Nginx running for everything that's in your cluster. You could do it per namespace, or you could even do a specific ingress that's just for your application if you know you've got this one that's super high traffic and you want to make sure it doesn't fall over. So there's a lot of options in that. More questions? Yes?
Is Kubernetes bound specifically to Docker, or can it handle other kinds of pods?
Right now, Kubernetes, actually I think technically Kubernetes isn't even bound to Docker anymore. I think it uses the Rocket container runtime, which is Docker compatible. But yeah, basically it can use at least any Docker compatible container runtime. I know that it's using Rocket right now. You can use Docker directly, and I think there are some shims for other ones out there, but I haven't played with them much. Yes?
I've been told that it's possible for Kubernetes to orchestrate containers across multiple locations, like maybe on-prem and cloud or multiple cloud providers. Number one, is that accurate? And number two, from a developer point of view, does that complicate calling services at all, or is that?
Okay, great question. So the question is, Kubernetes is capable of spinning up workloads and managing nodes and workloads across multiple cloud regions or cloud plus private data center or cloud to cloud. And does that complicate things as a developer trying to address your services? Yes, it can do those things because ultimately you just need to be able to network these computers together so that they can talk to each other and it can manage these things as long as it has the right permissions. So yes, it's capable of doing that, and as a developer, that's one of the other nice advantages is that it abstracts that away, right? Like if I use the service that we looked at here before, and we turn around and address this thing, Kubernetes knows where those pods are and how to route to them, and it's going to handle that for you. And all I have to worry about is hitting my API. So, all right, any last questions? We've got to wrap up here. Nope. All right, well, thank you very much for your time today. I'm Jeff Trent.